Hi guys, in this video I want to talk to you about rotational kinetic energy and kind of motivate where the equation comes from. So hopefully at this point I've shared with you either the demo or something to kind of motivate, like, hey, there is this energy storage mode where energy is stored in the rotation of some object. So flywheels are a pretty good application of this. If you have something that's like a wheel that's spinning really, really fast, you can slow down that rotation and basically transfer the energy to some other kind of energy, either to make something go up or to get it moving. And if something's coming to a stop, you can store that energy in some kind of spinning object and then get it out later. So it's just like some kind of storage mode. I'll return to this definition in a second, but I want to motivate where the equation for it comes from. And again, I'm going to kind of do a similar derivation to what we did for the rotational version of Newton's second law. So imagine I have some kind of really, really tiny mass. I'm going to call it a point mass, and it's moving in a circle. And yeah, it's moving in a circle. In this case, I don't need it to be accelerating. Let's just say it's moving in a circle at constant speed. And then I know that its kinetic energy is equal to 1/2 mv squared. But if I wanted to sort of think about what the rotational kinetic energy would that look like, I basically would want to rewrite this. I could rewrite this in terms of rotational terms. And I could think about the energy stored because of the rotation of this object, rather than just like thinking through it in terms of its linear motion. So sort of trying to put this in terms of rotational variables, I can rewrite the linear velocity, the linear speed, in terms of angular velocity and get omega r squared. That's going to be 1/2 m omega squared r squared. And I don't know if you see it. If I'm going to just rearrange this in a more suggestive way. This right here, this mr squared, is the rotational inertia of a point mass. So this right here, this term, is suggesting to us the rotational kinetic energy of this point mass. 1/2 I omega squared. And what I want to just generalize, I didn't show it, I'm not proving this, but this holds in general. The energy stored in some extended object is going to be proportional to 1/2 times the rotational inertia times its angular velocity squared. I want to say a few key points. Just like I did with F equals ma, and this derivation was very similar, and the ideas here are very similar. And what's the main idea here is this isn't anything new. This is just the this equation isn't anything new. This is just the rotational version of Newton's second law. So it is this formula, just looking at it through the lens of rotation. And similarly, rotational kinetic energy is just kinetic energy, just rewritten using the tools and language and lens of rotation. Now, there is a little bit more complication with rotation. So this is for a point mass. I showed it with one point mass. For a ruler, let's say, I have this ruler and it's spinning. Like that. This is, you can think of it as multiple tiny point masses. And they all have different rotational kinetic energies because they're all point masses, mr squared, mr squared. The mr squared is different relative to how far away they are from this axis. So, if I really wanted to sum all of them up, I would take mr squared times omega here, mr squared plus times omega there, and basically add it all up with the 1/2 in there. But what can be shown is, you can basically sum this all up, and when you do, like the total rotational inertia of an object, the thing that you would look up on a table, like the equation still holds. So it's not this equation doesn't apply to just point masses, it applies to in general. So EK rotation equals 1/2 I omega squared. I believe this is on your reference table. And it is analogous in the sense that it's 1/2 times like your rotational mass times your rotational velocity squared. So it looks very similar to our regular equation. This isn't anything new. It is just linear. It's just like plain old kinetic energy, but of these extended objects. They all have kinetic energy, and what the rotational formula does is it sort of sums this all up and puts it into one slot. Now, one final complication. If I have this thing rotating and moving, it's going to have energy due to the rotation and energy due to the movement of the center of mass. Just to kind of slow that down, I have an object moving. Let me just isolate the one motion. The center of mass is moving in a straight line at some speed v. It's going to have kinetic energy 1/2 mv squared and relates to the whole thing. But now if this thing is rotating, it has rotational kinetic energy 1/2 I omega squared. If it's rotating and moving, it's going to have both. I need to account for both. So this is kind of like a new slot. Ultimately, it's related to the kinetic energy of each individual point mass. But when you're looking at the overall motion of the mass, you want to think kinetic energy associated with the motion of the center of mass and kinetic energy stored due to its rotation of all those point masses. More concrete example. Check out my awesome Hot Wheels car. So this thing is moving along as the wheels are rotating. Those wheels have rotational kinetic energy in addition to the kinetic energy associated with the linear motion of this car. So it's moving a straight line, 1/2 mv squared. The wheels, 4 of them, have rotational kinetic energy 1/2 I omega squared associated with each wheel. That is rotational kinetic energy. Hopefully that was illustrative. Take care.